Okay, so we decided what's finite and what's infinite. The finite ones were the ones that stopped. The infinite ones had the dot, dot, dot. The third one we had to figure out because they didn't tell me what the terms were. I had to plug in 1, 2, 3 myself. By the way, is that one getting closer and closer to anything? As in the end behavior? 0, that's true. Yeah, end behavior is an important topic here, folks. So, if I wanted to find the first term, what do you think I should plug in? What? 1. Good job. 1 squared minus 1. And the answer is 0. If I want to find the second term, yes, we'll plug in a 2, and we get what? 3. I'm hoping that you see the pattern, that it's 1 less than a perfect square. So 0, 3, 8. We don't need to continue with that. However, if I want the 100th term, what do you think I'm going to plug in? 100. This is why an explicit formula is really more useful to you, because you can find any term you want. A recursive pattern, which you also talked about last year, a recursive pattern would require you to know, if you wanted to know the 100th term, you'd have to know the first term, the second term, the third term, the fourth term, the fifth term, the sixth term, the seventh term, all the way to the 100th term. Ain't nobody that want to do that. That's why the explicit formula makes it much nicer to go to any term you want. The recursive pattern is great for the first 5 terms. After that, it becomes a real pain. Here's the recursive one. Recursive one has 2 parts to it. As you can see, usually like there's a little breaks. I'm sorry, I didn't do a very good job. We got the starting point. We know that the first term is 3. Okay. It really bothers me when I ask for the first 6 terms and people skip the first term. I'm not sure why that happens. But yeah, you got to know where to start and, Then I've got a pattern to follow. What's the pattern telling me to do? You remember this from last year? Yeah, what are they telling me to add each time? No, don't get caught up in the notation, the little subscript notation. Remember, B sub n means like the next term. Equals. Now, keep in mind, folks, if B sub 1 is your first term, and B sub 2 is your second term, and B sub 3 is your third term, then somewhere way out in the list is B subscript n. What do you think is the next one after it? B subscript what? N plus 1. Right? And then there would be like n plus 2. What do you think is the one right before it? N minus 1. Do not get hung up in the notation. Understand that B subscript n minus 1 is the one before it. So the next term is equal to the previous term plus 2. So what's the rule telling me to do to find the next term? Add 2. Thank you very much. So what do you think comes after 3? 5. Good. and 7 and 9 and 11. This is fantastic for finding the first 5 or so terms. Horrible for finding the 100th term. I would not want you to use this to find the 100th term. I would want you to use an explicit formula. And you're probably saying to yourself, how do I get the explicit formula for this? Is this one of those cool ones that we studied last year? It is. This one's called an arithmetic function. What kind of function does it follow? You studied it in Algebra 1, Geometry, and Algebra 2. It's going up by 2 each time. What kind of function is that? Is it linear? You plug in a 1, you get 3. Plug in a 2, you get 5. Plug in a 3, you get 7. Plug in a 4, you get 9. Plug in a 5, I get 11. It is a linear function, right? It's got the same... So, it's got the same difference between the terms. In other words, we talk about it being a common difference. Man, that's large font. Okay. In this case, what is the common difference between the terms? Any term minus the previous term. What do you get when you take 5 minus 3, or 7 minus 5, or 9 minus 7, or 11 minus 9? It's 2 in this case, right? That's the common difference between the terms. Okay, a linear function. Now, common difference. What is another word for common difference? It's a 5-letter word. It starts with the letter S. Not sequence, plus those are little shiny things on the grid. Sparkle? No. No, I need 5-letter word, starts with an S. Something to do with the linear function, folks. Slope. That's what we need. The common difference is the same thing as the slope. Sequence. Sequence. It was a dad joke, okay? That's all it was, okay? Okay, sorry. Yeah, it was just supposed to be a joke, sorry. Gotcha. Slope. If this is a linear function, don't you think we can come up with a formula for this? Maybe something that looks an awful lot like the point slope form of the line that you guys know and love. Remember that?
Oh, that's it. And times.
So we've got the first term. You guys told me that slope and common difference were the same thing. That's your explicit formula that we talked about last year in Algebra 2. It's exactly the same thing as a linear function. I'll move it up. So do we know the first term? 3? Okay. Do we know the common difference between the terms? Hey, looks like we got a formula. An explicit formula. No, I do not require that you distribute the 2 and add like terms, which some of your Algebra 2 teachers were adamant about. I don't know why, but it's good enough the way it is. So, if you want the 100th term, what are you going to plug in for n? Yes, 100, thank you. Yes, I do realize 100 minus 1 is 99. And 2 times 99, that's 198. So what do we get here? 201? Yes, no, maybe so? Nobody wants to use the recursive to find the 100th term. We want to use the explicit, yes.
So then you don't have to subtract the 100.
Are you talking about using the zeroth term? Yes, you can use the zeroth term. The zeroth term in this case, which is not a part of the sequence, folks, is the term before the sequence begins. Can you tell me what that would be? It is 1. So what he's referring to is using like a y equals mx plus b version of the same thing, where the slope is 2, and the y-intercept is the term before the sequence begins. That's exactly what you would find if you distributed the 2 and added like terms. So yes, you can use that particular version, which would be the common difference times n plus a sub 0. You could use that, yes. We got 2 terms to understand here, converge and diverge. Whoa. The word converge means to get close to one single number. Gets close to one single number. Although some people think that diverge is just the motivation to jump into a swimming pool, it actually means not converging. So converge means we get close to a number. Diverge means we do not get close to a single number. Yes? Question? Oh, it was a bad joke. I know. Yes, question. Thank you so much. It is exactly like a horizontal asymptote. That is one possibility, but that's not the only kind of possibility. Okay? But that is one of the major ones. But converging does mean we have a limit. It's about end behavior. Okay, so what's going on with this first one? 1 over 1, 1 over 2, 1 over 3, 1 over 4. It's 1 over n. What is the limit as n goes to infinity? Ah, that is 0, right. So you just chose to tell me that it converges to 0. What about the next one? 2 over 1, 3 over 2, 4 over 3, 5 over 4. If you really needed a formula, it would be n plus 1 over n. What is the limit of that thing? Is it 1? Is this thing over time getting closer and closer and closer to the number 1? You got 2 over 1, you got 1.5, you got 1.3 repeating, you got 1.25, 1.2. What did I teach you about rational functions? What did I teach you? Take the largest power of n in the top, the largest power of n in the bottom, reduce it, and take the limit as n goes to infinity, right? That's because that's a rational function, right? And what does n over n give you? 1. So it converges to the number 1. What about the next one? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So you're saying the limit as n goes to infinity. Now we'll just use a sub n because, we don't want to take the time to worry about writing out the formula. You're saying it goes to infinity. Does that follow the word diverge or converge? Diverges. You know what? Yes? No, basically the plus 1 becomes insignificant because over time, think about if I put in 1,000,001 over 1,000,000. That little extra 1 is barely touching the numerator. So as n gets super big, it's not really affecting anything. You know what bothers me is when students say, it diverges to 5. Because right then and there, I realize, wait a sec, does this kid not understand that diverges means it doesn't have a number? Why are they saying diverges to 5? So I get really confused. Diverges means there's no number that it's getting close to. Look at D. -1, +1, -1, +1, -1, +1. It keeps doing this for a long time, folks. Is it getting close to a single number? No. So what does that mean? It's diverging. And so that's the example I wanted to give you, Miss Longmore, because you said, you gave me the typical one like letter C. But that one down there at the bottom also diverges because it doesn't get close to a single number. So we got converge and diverge. Do these really quickly. You should be taking these limits of these fractions, reduce them if possible, and see what happens. That's what you should be focusing on right now. Okay, so what's going on with the first one? Does it reduce? To what? 3. Therefore, you just told me what happened, right? It's converging to 3. All right, well, what about the next one? Can you reduce it? What can you get rid of? N squared, right? So now I have 5 over n. What happens as n goes to infinity? 0, right? Converges. What about the last one? What can you get rid of? N squared. So what happens as n gets bigger and bigger and bigger and bigger and bigger? It diverges. Hopefully that makes sense because we've done enough with rational functions that should not surprise you. We've kind of already talked about this, but we've got a couple examples to practice with. I don't like the way they've written out their arithmetic sequence, but we will modify it. So they want me to do a few different things here. They want me to find the common difference. Okay, so how do we do that? This is arithmetic, folks. So that means it has a common difference. This is going to follow the linear pattern like we talked about. Any term? What? It's 4. You were right. How did you find that? Okay, but you just, so you did kind of guessed and checked? No. Any term you want, minus the previous one. So I just randomly picked those two because they're positive. Because it was a nice number, that you could probably easily see that it was a nice number. Okay. I think it's a whole lot easier if we go down to the last one. An explicit formula. Remember that for the arithmetic? First term plus common difference times n minus 1. Unless you want to use your option there, Mr. Dixon. That'll work too. So what's the first term? -6, and the common difference? 4, and we're done with the question, or at least that particular part of the question. I just needed to know the first term and the common difference. Okay, now B, find the 10th term. What do you think I'm going to plug into that formula at the bottom if I want to find the 10th term? A 10. Now, I don't know what they expected me to do unless they just wanted me to keep adding 4, which I'm perfectly capable of doing, but I think is a useless exercise, in my opinion. So let's see, 4 times 9 is 36. 36 plus -6. Ah, that makes 30. Now, part C is the part where they want you to write a recursive rule. And the recursive rule, remember, has 2 parts to it. So what goes in the first blank? -6, yes. The first term is -6. How much are we adding each and every time? 4. Once again, that's only useful, in my opinion, for the first 4 or 5 terms. It's never going to be useful for the 150th term. Okay, so we're going to do the same thing this time, but with this next one, which is super duper cool. At least it is to me. How do we find the common difference between the terms? We got the natural log of 3, the natural log of 6, the natural log of 12, and the natural log of 24. How do we find the common difference? Any term minus the previous one, right? Oh, but you just had a whole chapter on how to combine those two things. Yes. No, it's not. I know it looks like it's a weird one. I grant you that, but it is arithmetic. No, you're adding the same amount every time. What you're about to show me is what you learned, or what you were reminded of, that you did last year as well. I need to know what property is being used right here with subtraction. What? I got to use the division, right? The 6 and the 3 are going to get divided. So how much are we adding each time? We're not adding 2, we're adding the natural log of 2. That right there is your common difference. And yes, I know that's weird, folks. Oops. Okay, let's go down and do this one. All right. The explicit formula. First term plus common difference times n minus 1. What's the first term? What is it? The natural log of what? 3. Okay. And the common difference? Natural log of 2. And no, I'm not going to ask you to distribute that. And no. They want me to find the 10th term. What am I going to plug in for n? 10. So what's 10 minus 1? 9. So this is the natural log of 3 plus 9 times the natural log, oops, I can't write, natural log of 2. What are we going to do with the 9? We're going to make it an exponent, that's right. King Julian reminded us of that from Madagascar. That's right, the move it property. We got the natural log of 3 plus... Well, he sang a whole song about it. Natural log of 2 to the 9th. You guys are going to watch the rest of this video, which I'm going to finish after school. So, jump back on right about at this spot, because this is the natural log of 512. And we know that we're going to multiply these two things together, giving myself the natural log of 1536. I'll finish that after school. All right, so we got natural log 1536 on that last question. We didn't, however, write the recursive formula, which would be kind of weird to write. Let's see, I'm going to have to switch to a different color so it's easier for the people at home to see. All right, so let's see here. 2 parts, right? First term, and we've got the next term is equal to the previous term plus something. So we've got to fill in these values. Well, obviously the first term is the natural log of 3, and the common difference that we're adding to each term is the natural log of 2. So that's my recursive formula. Just had to plug in those two things, just like we did before, with the nicer one from the previous example. All right, let's move on to the next slide. The geometric sequence. The geometric sequence is based on the exponential model. That's right, folks. The good old exponential model. You'll remember that the exponential model, y equals ab to the x power. Sorry, that's a little hard to see. for the geometrics, and I'm going to use G. I know they like to use A for everything, but I'm going to use G. G of n equals the first term times the ratio to the n minus 1 power. Now the reason they're using the n minus 1 power is because we're using the first term. In the exponential model, A represented the y-intercept, and the y-intercept is obviously when the x value is 0. Since we're not on the y-axis, we're not using the zeroth term, we're using the first term. That's why they had to subtract 1 from the exponent. So we're going to go through these examples here with these values. By the way, R represents the common ratio, kind of like common difference on the arithmetic ones. Man, I am hungry for pizza right now. That is for sure. Okay, so A, B, C, and D. So we're starting with 3, 6, 12, 24. How do you find the common difference? We take, let's go, R. R equals any term divided by the previous term. So 6 over 3 will work. And that means we're multiplying by 2 every time, which makes a whole lot of sense. Remember, I'm going to drop down to D and do the geometric, the explicit formula. And we need the first term. The first term here is 3. And the common ratio is 2. That gives you your explicit formula. Now part B asks for the 10th term. What do you think we're going to plug in? Of course we're going to plug in 10, right? 3 times 2 to the 10 minus 1 power, which happens to be 3 times 2 to the 9th, which should be really familiar to you because we just did 3 times 2 to the 9th, right? 2 to the 9th being 512. Should I double check that? What if I assumed that it was 512? It's really not 512, and one of my students gave me the wrong value. That would make me feel really bad. Whew, we're good. All right. And we're multiplying that by 3, so that's 1536, which should also be very familiar to you. Okay, so how do I do the whole explicit formula thing here? Remember that the explicit formula has 2 terms, or 2 different parts. One, we need to know where to start. In this case, we're starting with 3. We have the next term is equal to the ratio times the previous term. What is the ratio? 2. So there's really only 2 values that need to be filled in. The first term and the multiplier are the ratio. And those are G for geometric, right? G sub n equals 2 times G sub n minus 1. All right, let's do this with the same thing with these other values. We got A. We want to find the common ratio. So, any term divided by the previous term. Notice that I didn't choose any of the negative exponents to worry about. So guess what? We subtract those exponents, we get 2. So the multiplier is 100. Well, okay, so now we can write out the explicit formula, right? G sub n equals first term times the common ratio to the n minus 1 power. The first term would be 10 to the negative third. the multiplier being 100. Now, could I multiply that out and get the decimal version of 10 to the negative third power? Sure, I could. I don't need to, but I could. Now we can go up and plug in and find the 10th term, right? The 10th term would be 10 to the negative third times 100 to the 10 minus 1 power. So using my handy dandy machine, 100 to the 9th power times 10 to the negative third. That is 1 times 10 to the 15th power. C, the recursive formula. Don't stop moving around me now. Or I should say stop moving around there. First term, that's the 10 to the negative third. The next term is equal to something times the previous term. What is it? 100. Hopefully that makes sense. I never like the order they ask those questions. So, I've made a chart for you to kind of have in your notes. So for sequences, explicit sequences, a sub n equals a sub 1 plus d times n minus 1. The recursive one is the two-parter, right? A sub 1 equals a sub n equals a sub n minus 1. What? Whatever the common difference is. Sorry, I bled over into the next box. For geometric, we've got what we just wrote out. First term times r to the n minus 1 power. And first term, next term equals r times g subscript n minus 1. But these are the formulas that you're going to need from that particular section. And one of my students today pointed out that we could use the y equals mx plus b version of this, which would look like this. dx, or I should say dn, plus a sub 0. Now the only reason, you might have seen that in a different class, a sub 0 is the term before the sequence begins, right? A sub 1 represents the first term. A sub 0 represents the term before it begins. That's why this looks like y equals mx plus b. You can use that. There's nothing wrong with that at all. The second and the fifth terms of a sequence are 3 and 24. Find the explicit and recursive formulas for the sequence if it's arithmetic and then a geometric. So we're going to do this twice, once with arithmetic and once with geometric. So 1, 2, 3, 4, 5. So the second term is 3, and the fifth term is 34. Okay, so if we're doing this with arithmetic, how many times? 1, 2, 3 times are we adding d to get to 34? Starting with 3, and then we're adding 3 d's, right? 1D, 2Ds, 3Ds. So then we can solve this and get 3D equals 31. Divide by 3. Are you kidding me? Oh, that's 24. Gee whiz. I'm losing my mind. I thought, what in the world are we doing here? Okay, that makes a lot more sense, because if that's 24, which that makes that 21, and we divide by 3, we get a common difference of 7. Whew, that's a whole lot better. I can use that to go backwards and find out that the term before the first one, or I should say, the first term is -4. We needed that information so that we could write our explicit formula and recursive. So, a sub n equals first term plus common difference times n minus 1. And the recursive, a sub 1 equals -4. A sub n equals a sub n minus 1 plus 7. Those are the two formulas that you would find on the explicit and the recursive. Now, what if this was geometric? Then we're not adding each time, right? We're multiplying. So instead of adding d 3 times, we're multiplying r 3 times to get to 24. So we're going to divide by 3. And then we're going to take a cube root. And we find out that the multiplier is 2. So just like we did before, but now we're doing it with the geometric. G subscript n, first term times 2 to the n minus 1 power. What is the first term? Oh, I'm going to have to figure that one out, right? If my multiplier is 2, right, we had 1, 2, 3, 4, 5. We knew this was 3, and this is 24. And we are multiplying by 2 to go forward. To go backwards, we would divide by 2, right? So that means my first term is 1.5. And my recursive first term is, next term is something times the previous term. So our first term was 1.5, and we are multiplying by 2 every time. Okay. Let's see what's next. I think that's it for the notes. And you can work on homework problems from 9.3. I also am opening up a Math Excel for you to work on. And I'd like you to focus on the Math Excel so you can get more immediate feedback.